So for the second part of week 9, we're going to go over an introduction to some examples of statistical testing. And I would say that it definitely takes some reading of your textbook and looking at some of the videos that I've put in that in the course module to really kind of help out with understanding of these tests. And I'll go over some of the common tests that we use in research and the ones that you're probably going to read about the most in articles. So let's begin with the one you've probably all seen, right? That the way that we look at statistical testing is we look at number of variables. So bivariate test, we talked about chi-square. Chi-square start at a bivariate level. So what's the association with salary and happiness, right? We can't give a predictive relationship, but we can look at that association between two variables. We're going to learn about regression, and using multiple regression, we look at what are the factors that predict, job satisfaction. Is it the independent variables of salary? Is it, receiving merit-based awards? Is it collegiality or respect from coworkers, right? We're testing a lot of independent variables that predict that job satisfaction outcome or dependent variables. So think of it that way. Am I looking at two variables, or am I looking at a relationship of 3 or more? And then level of measurement, right? We'll talk about parametric and non-parametric, but if you look at chi-square odds ratios, typically if you have variables that are at the nominal level, so they're named or they're dichotomous, they're yes, no, or they're ordinals, you can rank them. So a high, medium, or low, those variables are acceptable for chi-square and odds ratio. When you're going up the kind of testing ladder, parametric tests are more picky, and they won't, they're not, I'm personifying them, they're really not picky, but you need a higher level of measurement. So interval or ratio level measurement, and they often require that a stipulation is that there's a normal distribution or a distribution that's not skewed. Remember, we looked at skew. So examples of parametric tests are t-tests. So a lot of t-testing, especially in psychology, in pre and post test design, and in experimental design, we do a lot of t-testing and linear regression. And I'll show you both of those in a bit. So you want to know how many variables am I testing? And then again, what's my LOM, my level of measurement, right? And those are the things we're looking at in terms of kind of deciding which test is appropriate. And again, chi-square, you're going to see everywhere. If you think about it, a lot of the things we measure in health sciences may be nominal or ordinal level. So chi-square allows us to look at those differences. Again, chi-square will not tell you if there is a direction or if there is causality. It just tells you association and patterns of association. And in the next slide, I'll show you a crosstab that we produce through statistical software. And the whole deal of chi-square, it's like, we would expect these values based on some information that we have, and then do the values that we observe, do they differ from expected? And that's the whole deal with it. If you expect a certain percentage or proportion to be in one of the cells of the crosstab and it looks different, then you say that there's a difference between expected and observed. And you have to examine the data. And I'll show you in this example, right? We have a fictitious virus, right? I know we're all kind of virused out, right? We're like, no more, right? But let's use this example. So here we have this fictitious virus, and we expect that 10% of people get it. So if it doesn't matter by gender, we expect that 10% of men should have the virus, and 10% of women should have the virus, right? And that 90%, the other 90% should be well. So here, right? In the population, we think 10% should have the virus, 90 should be well, and it should be equal among men and women, right? There should be no difference. We expect it to be 50-50. Let's look at what really happens. These are the expected, right? We're calculating the expected. So we're saying there's no difference of gender. So here out of the 50, 5 people or 10% of the 50 should be exposed or have the virus. 5% of women should have the virus. 45% of men and 45% of women should be virus free, right? We expect that, right, the virus only 10% of the population is affected. What we see, right, in reality, we see that the real results are that 0, so no men have the virus. All the men, right, the 50 men are virus free, yet unfortunately, we expected only 5 women to have the virus, but 20 women have the virus, right? Great, right? Just what we want to see. And here we expected 45 women to be virus free and 30 were. So what we see right here in this area, which I'll annotate, right? You know, I'm into the annotations, right? Right here. Let's see, I'm going to take a different. Right, what we see right here, this group got hit the hardest, right? We expected this to be equal, 5 and 5. What we found is that, you know, 4 times as many women had the virus as we expected in this group. Ooh, sorry. So what we need to do, and this what you see, this output comes from a statistical package, right? So it's a statistical analysis software package called SPSS, statistical it's a statistical analysis, right? And what you see here, right, unfortunately, it's a different relationship, but what you're seeing, and focus right on this piece here, the chi-square, the values are really hard to interpret. You look at the significance. So is there a significance here between age group and smoking? Right, and if we look, what do we see in terms of patterns of smoking? So who's smoking the most? Right, look across and see the percentages. We see that smoking every day, we have, wow, right, 56.6%, 53%, wow, 39.2%, right? But then we look at older adults, we have less smoking. So we have a large percentage of people smoking every day in these 3 groups. And then if we look at a larger age group, we have majority of people not smoking at all. So very interesting. We say, like, that looks like a difference. So if we visually scan this, we might think that these age groups are smoking less, more frequently, and this age group is smoking less. But is that significant? We have to check it out, and we see it. Right? We see that not only is it significant, it's significant at the highest level. This, if we did it, would get 3 asterisks. So we see the relationship. It looks visually like there is one, but we can't rely just on the percentages in the table. We have to look at the p-value. And odds ratios are really, really great. Odds ratios, and if you want to read a little bit more, it's going to be in chapter 10 as well. But they look at, similar to a chi-square, they look at the relationship between exposure and outcome. And what you really look at is, what's the odds ratio? So if the odds ratio is greater than 1, it means the group you're comparing is, less than 1, means the group you're comparing is less likely to have a characteristic. So, and we'll look in the tables. If an odds ratio is 0.8, it means that the group that you're looking at is less likely than the group you're comparing to. When you have an odds ratio of more than 1, it means that that group is more likely to have the condition or characteristic. So when you get a high odds ratio, you know, we used to use it a lot when we looked at exposure to lead. So people who are, you know, live near bridges, right, which had a lot of lead paint, and we looked at the odds ratio of asthma. We found the odds ratio of asthma for people who lived close to bridges, right, with this toxic paint. The odds ratios were 10, 11, 12, right? It's very high. So the risk or the exposure or the instance of people living next to those bridges getting having asthma was much higher. People who lived away, you know, let's say in an area that was very forest dense, right, their odds ratio might be 0.8. So they were at much less risk of developing asthma than people who lived near these bridges that were just shedding all of this paint with lead. Here, another interpretation, we're looking at children with ADHD, and we find that they have 3 times the odds of having an elevated aggression level compared to those who do not have ADHD. So that odds ratio means that the risk or the odds or the exposure to that condition is much greater. So you're always looking, when you're testing for something, you're looking for a high odds ratio. That's what you're looking for to see the difference. But if you have an odds ratio less than 1, then the odds of having that condition are lower. And just take a minute and look over this table and get familiar with what the content entails. Right, we have the prevalence of, and if you look at the bottom, it's the health status of adults on the autism spectrum. So they're looking at the co-occurrence of 2 things, right? They're looking at adults with autism spectrum disorder and controls. And then they're looking at both of these groups and they want to see, okay, so in these 2 groups, what's the risk or the exposure or the likelihood, right? Let's go back and see what's the 3 times, what's the odds of someone having this other condition being an adult with ASD or a control. Right? They looked at alcohol abuse, dependence, anxiety, attention deficit, bipolar disorder, dementia, depression, drug use, drug dependence, OCD, psychoses, schizophrenia, and suicide attempts. And they tell you in the table what statistics they're calculating and what the terms are. And we see here, we want to know first with the chi-square, is there a statistically significant difference in the presence of these conditions within adults with autism spectrum disorder and those who are controls? And I want you to scroll down, right? You can see that for most of these factors, right, most of these psychiatric conditions, there's a statistically significant difference in adults with ASD versus controls. The only 2 items, and I'm going to use let me use the pointer again. Let's see. I'm going to annotate really quickly. And let me just, this here, you see this one? Oh, right here, there we go. Oops, sorry. Right, these 2 are the only 2 items that are not statistically significant, which means that when you look at the 2 groups, that relationship doesn't pan out. Where we look at alcohol abuse, dependence, anxiety, attention, bipolar, dementia, and then we stop and we go to OCD, psychoses, schizophrenia, suicide attempts. Those differences in adults with ASD and controls are statistically significant, right? They're more than just chance. And if we look here, we're going to look at the odds ratios, right? We want to look and see, okay, what's the difference, right? Which puts the group at the highest risk, right? Go back and we'll look here. Oh, sorry, one sec. Right, children with ADHD have 3 times the amount of elevated aggression. So we're going to go here and let's look. Let's take the highest odds ratio. You see how they're done, which is interesting, right? They're done in almost numerical order. So look at these two. Look at these. Wow, look at these 3 numbers here. Let me just give you a annotation real quick. Right, look at these. Look at these 3. So what this is saying, if you interpret it, you're saying that if you are an adult with ASD, you are almost 15 times as likely than the control, right, to have OCD. You're almost 12 times as likely to have other psychoses. You're 22, right, 22.24 times, as likely at, or at odds to have schizophrenic disorders, right? Think about that, right? That it's really important that we understand how these things occur, right? We'll go back just so you can see it. Oh, sorry. I'm going to go back 1 second. I want to show you, right? 3 times the odds. Look at this. This is incredible, right? Sorry, 22, right? Adults with ASD are 22.24 times as likely to have schizophrenic disorders than those who do not, right? That those adults who are controls or do not have ADSD. Think about that, right? What a way to quantify and predict. And remember, we talked about t-tests. T-tests like chi-squares are done all the time. In a lot of the articles you've read, I know that you've talked about t-testing. And there's kind of 2 varieties. So you're looking at groups and saying, do the groups differ, right? Does the mean scores of the groups differ? Are they really, they might look different. They might have different average scores or mean scores, but is that really statistically significant, right? That's the basis. And if you have a t-test, an independent t-test, you're testing 2 groups, right? 2 groups that should be independent. So think about experimental and control groups. These 2 groups should be very different and they should be very independent and separate. Therefore, you do a t-test that is an independent t-test. And you want to see if there's a difference between groups. And think about it this way. If you have more than 3 groups, it's called a nova. A nova is another. It's like a beefed up t-test, but don't worry about that right now. Just get the difference. When you have a t-test, it's 1 group. So what you're doing is you have the same group of people and you're testing them pre and post, right? So if I'm doing an experiment, I'm doing an independent t-test. If I'm doing a intervention and I'm, 8 weeks of training for, Tai Chi to reduce stress for employees that had worked during the COVID pandemic, right? Pre and post testing, 1 sample, you're testing them pre-intervention, post-intervention. It's a paired samples t-test. So you either have an independent for 2 independent groups, or your pre and post testing, that's your paired. And we'll talk about regression, and there's so many types to address. Some regression uses 1 variable, and most regression models use multiple independent variables. And I'm going to say this now, and I'll say this again, that, the world is complicated. It's more often than not that if you look at an outcome, it's not just caused by one thing. There are many things that predict an outcome. So regression says you can kick in a lot of independent variables and see how they each have an effect, and then have effects together on your dependent. So in regression, you have a lot of independent variables and you're looking at dependent. But the first type of regression I'm going to show you is the most basic. It's a one-to-one relationship, right? One independent, one dependent variable, right? And we look to see the R-square score just says how well the relationship is, right? This line you see is the perfect relationship, and then we see how close the relationships of variables work together. Here they're doing age and blood pressure, which we see a lot, right? As people get older, blood pressure goes up. Some people think that's okay, and it's not pathologic, right? That it's okay. Other people pathologize high pressure with age, and really, have the same markers across the life course. But that's a whole nother direction, right? If it's a positive relationship or a negative relationship, right? Is it inverse where one variable increases and the other variable decreases? Do they both increase or decrease in the same direction? So you're looking to see the relationship. Here we see that there's a direct relationship that as age increases, blood pressure increases as well. Logistic regression, but I want to see, let's see, I want you to see, oh, okay. Logistic regression is an interesting one. Logistic regression, oh, sorry, it's called logit, but what it does is it takes a variable and makes it dichotomous or nominal. So you're looking to see if somebody is satisfied or not satisfied with their service at your facility. You're looking to see if somebody, did they pass the screening at the end of your intervention? Yes, no, right? It's really beneficial in many ways. And it's helpful because, and I'm going to give you this answer and I want you to think about why. Sometimes you want to really look at a lot of variables in relationship. You want to do regression, but you don't have an interval or a ratio level variable. So what do? Right? You want to use a variable, but it's only nominal. So instead of not doing regression, you can use a nominal level variable as an outcome in logistic regression. And here's logistic regression. It does what we love to see. Look what it's doing. It's adjusting odds ratios. So it's reporting the outcome as more likely or less likely than less likely exposure. And there are a couple things circled, right? The researcher said, we've employed multivariate logistic regression to test the association of a parent-reported professionally diagnosed lifetime history of maternal mood disorder with a child with autism spectrum disorder over another diagnosis, over, I guess, an autism diagnosis by specific mood disorder. So they're looking at if the mother has had these conditions, what's the odds? Is the odds of getting autism spectrum, let's see, are higher with higher functioning autism. And this is, I guess, is autism. So you're looking to see what's the odds ratio, right? What's statistically significant? What is significant here? First, before we interpret anything, we have to find significance. If it's not significance, we will not interpret it. Oh, sorry about that. So let's look and see. Let's see who's significant. Yeah. Oh, sorry about that. Let's clear. Significant. Significant. Not significant. Not. So we may want to talk about all these other variables, but the only things that are significant are these three. So we know that having a mom who had bipolar disorder will increase your odds of having autism spectrum over autism. Right? Same thing, maternal depression. So it seems like maternal mood is really playing a high role here, but this is less, right? So if you have a mother who has maternal depression, the odds of a child having autism spectrum versus autism is 1.62. Right? These are at only these are the lowest level of significance. We look here, this is more significant. So interesting, the child age predicts the likelihood of having, Asperger's syndrome versus autism. So very interesting, right? We're looking at what is significant. And then let me get rid of these, I'm sorry. Multiple regression is the most commonly used, and I'll tell you why. It requires different levels of measurement, right? You can change variables and use nominal level variables that you make dichotomous. You can use interval ratio, you can use some ordinal. It allows you to look at the dependent variable and to bring in a lot of independent variables that might impact the dependent, right? So you can control and say, well, I want to control for gender, I want to control for age, I want to control for whatever you want to control for, and to make sure that relationship you find is real. So this is something we'll talk about more and more, and I want you just to see the difference here, that continuous is interval or ratio and categorical is nominal or ordinal. So if you're looking at a test and you say, can I do it? You can go in and say, oh, okay, I can use nominal or ordinal for chi-square. That's great. T-test, I need, well, so t-test look dichotomous, continuous, right? Continuous, I need interval ratio, higher level of data. Multiple regression, dichotomous or continuous, this is the independent variable. Right, and then logistic regression here, just think about this, you need the dependent variable to be dichotomous. So right now, I don't expect that you would understand all of the different tests and when they need to be done, but I want you to see the concept of, if an article you read is reporting one of these tests, right, chi-square, do they have nominal or ordinal? If they're doing t-testing, do they have interval or ratio? If they do multiple regression, right, let's look at right, do they have interval ratio level dependent variable, right? Do they have a dichotomous variable as the dependent variable in logistic regression, right? What are they using? So this is a good handy reference. It's not something we memorize. Over time, you'll become more familiar with it, but you look at the number of variables here, an independent, the type of data for the independent, the type of data for the dependent, and control. So it's something to think about when you're reading the articles for your assignment, which I'll talk about in a little bit, but you want to think about, when they talk about a t-test, do they ever talk about level of measurement, or does the variable match that level? So just think about it. Think about how level of measurement and statistical testing and significance work together.